Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. And today I'm wrapping up section 8.5 of chapter 8, which is on computation. And there's only going to be one more video I'm going to make on this chapter. That's going to be on section 8.6, which is on quantum computing. I'll do that one next time. Anyway, today I'm wrapping up computational complexity, and I'm going to talk about a very important unsolved problem, namely P versus NP. As a matter of fact, this is one of the 7 Millennium Prize Problems, one of the 6 that hasn't been solved yet. One of them has been solved by Perlman, but there's $1 million prize for anybody who can either prove or disprove that P equals NP. And who knows, maybe it'll be one of you. But anyway, let's begin. So, what does this problem say? Well, here's what I say about it in the book. I'm not really going to dwell on this slide. This is just what's in my book. I'm a little bit of a novice on this, but I took this slide from the web. I think this gives you a lot more information about this problem. So I have to tell you what these things mean, what P and NP mean. P is just a class of all problems that can be solved in polynomial time. There's a deterministic algorithm for solving it in polynomial time. And I talked about polynomial time last time. That just means that the running time is O of x k to the n, where k is the size of your input, the number of bits of your input. And I think I told you some problems that are p. Basically every arithmetic operation we do, like addition, subtraction, multiplication, division, no matter how large the numbers are, no matter how large the input. If your problem is just to do some arithmetic, then that's P. That's easy. P problems are considered easy, by the way. And not just arithmetic, but it turns out there's a lot of other algorithms that are P. Like I think I mentioned last time, it was proven in 2002 that primality testing is P. That was a pretty groundbreaking result. And I think a lot of other, important computational problems are known to be P right now too. But there's also problems that are harder. P are the easiest. But then there's things called NP. NP stands for non-deterministic polynomial time. That means that there's no deterministic, as far as we know, there's no deterministic polynomial time for solving some of these algorithms. I think P includes NP, by the way. Yeah. So NP, yeah, P is part of NP. So NP includes P. NP just means that there exists a sort of a Monte Carlo algorithm, if you like, non-deterministic. That just means it's not really a computer algorithm because all computer algorithms are deterministic, at least with classical computers. But you might be able to run some random, simulations like rolling dice or something, and you might be able to solve the problem in polynomial time using probabilistic methods. I can think of some examples like that. Primality testing used to be like this. I mean, there was this thing called the Rabin-Miller test. There were these numbers called pseudo likely primes or likely, um, you know, we didn't actually have a proof that they were prime, but they were very likely to be prime because if they satisfied the Miller-Rabin test 20 times, and it was, probability was essentially zero that they wouldn't be prime, but it wasn't really a proof. So those are examples of NP problems. I can't really think of any other ones off the top of my head. But I guess, and then there's other problems that are even harder than NP. There's problems that are called NP hard. NP hard just means these are the hardest problems there are. I mean, these are problems like the traveling salesman. I mentioned the traveling salesman problem last time. That's one of the hardest algorithms we know of. Trying to find the shortest possible route connecting a list of cities. If it's a large list of cities, the running time is exponential in the number of cities. So if you wanted to do 1,000 cities, you'd have to wait longer than the age of the universe to do it. It doesn't mean they're not p. See, the kind of exciting thing about this problem is that if p equals np, that means that all these problems that we think of, I think just about every problem we know of is NP. Um, but if P equals NP, so another thing I have to tell you about NP. This is the way I understand it anyway. NP problems. Here's what we do know about NP. If we solve an NP problem, we can check that the solution. We can verify the solution in polynomial time. A good example of that is factoring. So it's not known that factoring is P. As a matter of fact, I think most computer scientists believe that factoring large numbers is not P. And our internet security depends on that fact. Actually, if we ever discovered a polynomial time algorithm for factoring large numbers, it would make RSA obsolete, and then all of your computer security would be insecure. People would be able to steal all your passwords and all your bank information. That would be very bad. Good news is that maybe we'll switch to quantum computers. There's two pieces of good news, actually. First of all, factoring may not be P. Yeah, even if it were proven to be P, we'd still have to find an efficient factoring algorithm. There's other types of cryptosystems we could switch to if it turns out somebody figures out how to do factoring quickly. But what I'm trying to get at here is the reason this P versus NP problem is really important is because it would mean that if P equals NP, which is shown on the right, that would mean that every problem that can be checked in polynomial time can also be solved in polynomial time. Like Rubik's Cube. I think a Rubik's Cube is another good example. I don't know how many guys have solved a Rubik's Cube. They're really, really difficult unless you know the trick. There is a trick. I think at one time I knew how to solve a Rubik's Cube in about 5 minutes. I forgot the trick, but first time I had a Rubik's Cube, I worked on it for I think all night, and I only got maybe one side. It's a very, very difficult puzzle to solve, as I'm sure you guys all know if ever tried to solve one. But you can mix it up in just a few seconds. I mean, ideally you'd be able to do just the opposite of what you did to mix it up. So check. I mean, that's sort of like checking that it's solved, or maybe factoring is a better example. It's very easy to check if you factored a number into its prime divisors. So you had a huge number, which is what they use for RSA, say a 600-digit number that's a product of two 300-digit primes. Well, they're almost impossible to factor. We don't know any factoring algorithm that can do that within the age of the universe. But if we did factor a number like that, it would be very easy to check that this is correct factorization because it's very easy to multiply two primes together. It's also very easy to test that the numbers are prime. So I think you get the idea. These are, cryptography depends on what are called one-way functions. And a one-way function is a function that's very, very difficult to solve, to calculate the value of the function in one direction, but calculating the inverse is very easy. In other words, solving is very difficult, but checking that is correct is very easy. So it would be bad news for cryptography if P was equal to NP. If somebody proved that P was equal to NP, that would mean that at least in principle, every classical crypto system, in other words, every crypto system that uses a classical computer to solve. I'm not talking about quantum computers now. That's another ball of wax, but just classical computers, which is the computers that most of us are familiar with. And by the way, quantum computers are still in their infancies. Nobody's built a practical quantum computer yet that can solve useful problems. That's probably another 20 years or so from now. But at least with classical computers, if it turned out that P was equal to NP and somebody figured out how to solve every NP problem in polynomial time, that would be very bad news for cryptography. That would basically mean that there's no secure crypto system and there's no way to keep your private information secure over the web unless we switch to quantum computers. So just a little heads up on that. But we don't even know that P does equal NP. And I think most mathematicians believe they're not equal. I think the consensus is among most mathematicians that there are problems that are NP but not P, meaning that they're easy to verify but they're almost impossible to solve. So anyway, that's a little overview of P versus NP. If any of you guys think you can tackle P versus NP, prove that P either equals NP or is not equal to NP, if you can prove that, then you'll get a $1 million prize from the Millennium Prize Problem Foundation, and I'll be very proud of you too. So anyway, just that concludes my video for tonight on P versus NP. Thank you for watching. Long live math, and I'll see you guys next time. Bye.